go to our next section, 9.5, alternating series. Alright, let's look at the theorem. We will use this theorem a lot in the next few examples. So this is called theorem 9.14, alternating series test. Alright, so let's a sub n greater than 0, the alternating series sigma n from 1 to infinity, negative 1 to the n a sub n. So if you have negative 1 to the n, the term will alternate negative, positive, all the way, alright, until infinity. And another one is sigma n from 1 to infinity, negative 1 to the n plus 1 a sub n is converges when two conditions are met. So you have to check these two conditions and both of them have to satisfy. Alright, the first condition is limit as n go to infinity, a sub n must equal to 0. The second condition is a sub n plus 1 must be less than or equal to a sub n for all n. So you have to simplify the second condition and make sure it's whole, and this first second has to be whole to be converges. Alright, let's look at the example. Alright, let's look at our first example. I have sigma n from 1 to infinity, negative 1 to the n, 3 to the n. So I have to put in this general form. So I will rewrite this. I can rewrite this as negative 1 to the n, and then a sub n. So my a sub n would be, I'm sorry, I forgot to put the n here. Should be n right here. Alright, now it's in the right form. So, so my a sub n is 1 over 3 to the n. So I'm gonna test the first condition, which means I'm gonna take a limit as n go to infinity. So I'm gonna take a limit as n go to infinity of 1 over 3 to the n, which is my a sub n. So as n go to infinity, you will see this equal to 0. So the first condition satisfied. Now I'm gonna check the second condition. My second condition, I have to find a sub n plus 1, right? So my a sub n plus 1 will be 1 over 3n plus 1. As you can see, 3 to the n plus 1 is bigger than 3 to the n. So my a sub n plus 1 is smaller than my a sub n. So a sub n plus 1 is smaller than a sub n for all n. So by the theorem 9.14, this is converges, right? Now let's look at my second example. I have this series. So again, if you're going to put in this form, your a sub n will be n over 3n plus 2. I'm going to test the first condition. I take a limit of a sub n as n go to infinity. So this step I did is I divide numerator and denominator by n. So I have n over n, 3n over n plus 2 over n. N over n is just 1. And this is 3 plus 2 over n. And as n go to infinity, you're going to have this term will be 0. Alright, then you're going to have 1/3. So it's not equal to 0, so the first condition is failed. We don't satisfy the first condition. And if you recall theorem 9.9, n term test diverges. So it said that if limit of a sub n not equal to 0, and then the series is diverges. So this whole thing is diverges. Alright, so let's look at the next example. I have a trig function here. So I have sigma n from 1 to infinity, 1 over n cosine of n pi, and n is an integer. So I make a little table here. When n is 1, you're going to have cosine of pi is right here, so it's negative 1, right? Now when n is 2, you have cosine of 2 pi. Cosine of 2 pi is over here, which is 1. And you're going to keep on to 3 and then 4. So basically this is just negative 1 to the n, alright? And 1 over n is just this one right here, but cosine in pi is negative 1 to the n. From here, my a sub n is 1 over n. My a sub n plus 1 is 1 over n plus 1. As you can see, the denominator is bigger, so this whole fraction is smaller for all n. If I take a limit of a sub n, my a sub n is 1 over n, I get 0. So the first condition satisfied. Now, yeah, I did prove both. So the second condition is right here. This is the first and this is the second. So it converges, right? The next theorem is theorem 9.16, absolute converges. So if the series sigma absolute value of a sub n is converges, then the series sigma of a sub n also converges. Let's look at more theorem and example. Alright, let's look at our last section of 9.5. Alright, this is a definition of absolute and conditional convergence. So let's look at the first one. The series sigma a sub n is absolutely converges when sigma absolute of a sub n is converges. So if you can put in the absolute value and you prove that it's converges, so it's absolute converges. So let's look at this example, number 4. I have this series, alright? So if you put in the correct form, my a sub n is 1 over n squared. And if I put a sub n in the absolute value, you can see that using p series, my p is 2, which is greater than 0, then it converges. So this whole thing is converges absolutely. Now the interesting part of this next example is I have this series, alright? My a sub n is 1 over n to the 1/2. First method, I'm going to use alternate series test. If you take a limit as n go to infinity, 1 over n to the 1/2 is going to be 0. My a sub n plus 1 is just 1 over n plus 1 to the 1/2, which is less than a sub n for all n. So the two condition is satisfied. So if you use alternate series test, it converges. Now, however, if somebody else or your test use different test, you use p serial test. You're gonna have sigma n from 1 to infinity, 1 over n to the 1/2. My p here is 1/2, which is less than 1. So by using p series test, it said that it diverges. So sometimes that if you come across by using two different tests and give different result, you will conclude that it converges conditionally. Alright, see you later.